Chapter 5 is all about integers, and section 5.1 is the addition and subtraction of integers. So in this section, we're going to make sure that we understand what integers are and that we can explain them. We're going to go over a couple models for how to carry out addition and subtraction with integers. And then we'll also talk about some of the properties for addition and subtraction, specifically about integers. Now, up until this point, we've only worked with whole numbers. Whole numbers are positive, and they are not fractions, they are not decimals, they're whole positive numbers. In this section, we are starting to talk about integers. Integers include all of our positive whole numbers. So these are the numbers that we've worked with up until now, positive whole numbers. And in this section, we're going to refer to these as the positive integers. The negative integers are the opposites of positive integers, meaning that it's almost like a mirror image where you can swap over to the other side of the number line. So 2, that is a positive integer. Negative 2 is the opposite of that. And we can see that because negative 2 is 2 units away from 0 to the left, whereas positive 2 was 2 units away from 0 on the right. So 2 and negative 2 are opposites. And we could do this with every positive integer. We could find a positive integer and then map it over to the left-hand side to find the opposite, or the negative integer. Something to notice about our number line, we used to start at 0 and just go forward, and the numbers would become larger as we move to the right. Now that our number line goes further to the left of 0, we're going to say that these numbers get smaller as we move to the left, or more negative. This can be confusing because sometimes when we want to compare numbers like -5 and +5, you might think that they're equivalent in value because they both have 5 in them, but one of them has a negative, meaning it is much smaller. It's the opposite. Or another comparison, so if we looked at -5 and +5, +5 is larger. If we looked at -5 and +3, a common mistake would be to say that -5 is bigger, but it's not. -5 is further to the left, so it's smaller than +3. So if you wanted to compare two numbers, you're going to want to visualize where they are on the number line. The further left a number is, the smaller. The further right a number is, the larger. So comparing two numbers, you would just locate them on the number line. Whichever one's on the left, that's the small number. Whichever one's on the right, that's the larger number. Now that we know what negative integers are and positive integers, we can create the set of integers, which in our textbook, they're referring to the set of integers with a capital boldface I. I is the set of all the negative integers. I'm using these ellipses here to say that this list continues leftward. So all of the negative integers, including 0, and then also all of the positive integers. And again, I'm using ellipses here to say that this list continues to the right. So now we have a couple different sets of numbers. We have the whole numbers, that's 0, 1, 2, 3, 4, 5, etc. We use a W to represent the whole numbers. And now we have the integers, which has all of the whole numbers inside of it, but adds the negative integers to it as well. One of the models discussed in this section is a chip model. So a chip model is best when you have a physical manipulative, like colored chips, like red chips and white chips. Now the textbook is using black and red chips, but since I'm using a black background, you wouldn't be able to see black chips if I drew them. So I'm going to use red and white chips. My white chips will be positive integers, and I'll just draw my white chips like a circle. And then my red chips, those are going to represent negative integers, and for those I will just draw a red circle to represent that chip. Now anytime we have a red-white chip combo, they would zero each other out. Let me show you what I'm talking about. In order to do this integer addition, we first need to practice representing numbers using chips. And the book does this on page 221. So if you wanted to follow along with the book, that'd be great. If we wanted to represent the positive number 2, like they did in the book, we could use 2 positive white chips because 2 is a positive integer, and their 2 positive white chips is equivalent to 2. However, we could add neutral pairs and still find a net value in our model of 2. So if I were to add a neutral pair, like another white chip and another red chip, this still comes out to 2 because the red and white chip pair that I have here in the yellow circle, this is neutral, so it's equivalent to 0. So if I want to, I can continue adding these neutral pairs, and the value in the circle would still be 2. So I could add another neutral pair if we want to. In fact, I'm going to add 2 neutral pairs. So I've got 2 negatives. If I want neutral pairs, I need to match those up with 2 positives. Since every red dot that I added also had a white dot to pair with it, I basically added 0 to my model. So what's in the circle is still a value of positive 2. Okay, now that we know how to do the chip model, or how to represent a single number using the chip model, we can practice doing some addition problems. For example, maybe I want to do something like 2 plus negative 1. So this is integer addition. I've got a positive number added to a negative number. What I would do is represent my positive number with white chips. So I've got 2 white chips. I could use any representation of 2 that I want, but there's no need to add extra chips here, so I'm not going to bother. And I'm also adding 1 negative chip. So I've got my negative 1 here in red. So for the chip model, you represent each number with the appropriate color, if it's positive or negative, and then you go back and check for any neutral pairs. If you have a neutral pair, maybe circle it, or if you're working with physical manipulatives, you could just take it out of the picture. Once those are gone, you're left with exactly 1 positive chip left over. Which means the sum 2 plus negative 1 equals positive 1. We can do this with other negatives too. Let's try another one. Let's do negative 3 plus 2. So I'll start off by representing negative 3 using red circles. Then I'll represent positive 2 with white circles. Then I'll go back and look for any neutral pairs. I have 1 neutral pair here, 1 neutral pair here. After I've removed my neutral pairs, I'm left with 1 negative chip. Meaning negative 3 plus positive 2 equals negative 1. Let's try another one. how about 4 plus negative 3? So I'll do 4 white chips, 3 red chips, look for neutral pairs, remove them because they are worth nothing, and then take note of what's left. 1 white chip, meaning our answer to the addition problem is positive 1. Another model, which is quite similar to the chip model, but doesn't require the physical manipulatives, is the charged field model. Positive integers are represented with a plus sign, negative integers are represented with a negative sign, and any positive-negative pair is just like the red-white combo. It neutrals out and it's a 0. So again, if I wanted to represent the number 2, I could do that with 2 positives. But I could also add any amount of plus-minus pairs I want, and it's still keeping the net value in this circle 2. Because every one of these plus-minus combos is like a big fat 0, and it doesn't affect the overall value in the circle. So I could remove every plus-minus combo I've got and see that I'm still left with 2 positives. I like this model because you don't have to have the physical chips with you, and you can still illustrate things like addition of integers. So 2 plus negative 3, I would draw 2 positives. I would draw 3 negatives. I would look for neutral pairs. Once I found them, remove them. Take note of what's left. We have 1 negative left. So 2 plus negative 3 equals negative 1. Very similar to the chip model, but we're using plus signs instead of white chips, minus signs instead of red chips. This pattern model is also pretty useful. We know how to add whole numbers, so things like 4 plus 3, we already know that's equal to 7. 4 plus 2, we know that's equal to 6. 4 plus 1, we know that's equal to 5. 4 plus 0, we know that's equal to 4. Now looking at this, I want us to recognize a little bit of a pattern. I'm always adding 4, or starting with 4, sorry. But the number that I'm adding is decreasing by 1 each time. So I started off by adding 3, then 2, then 1, then 0. And look at what happened to the sum. It's counting down. 7 to 6, 6 to 5, 5 to 4. So if we were to add 4 plus negative 1, we could say let's just continue the pattern, which would be 4 plus negative 1, we need to go down from 4. That would become 3. 4 plus negative 2, that would come down from 3, that would be 2. 4 plus negative 3, come down from 2, that would be 1. 4 plus negative 4, come down from 1, that would be 0. 4 plus negative 5, come down from 0, that's to the left of 0, we'd get a negative 1. 4 plus negative 6, come down from negative 1, that would be a negative 2. Now there's something I want to point out here. Notice that there's a few of these sums that we're doing that come out to still be positive. Now, of course, adding positive numbers, so we've got positive plus positive, right? That should always equal a positive number. But then we move into this phase where we're adding a positive number and a negative number. So we have positive plus negative. These still came out to be positive. But then if we kept going, we found that there's some positive plus negatives that give us negative numbers. And that's because the negative number was larger, further away from 0 than the positive number. So here between 4 and negative 5, negative 5 is so far away from 0 that it pulled the positive 4 over to the negative side. Whereas up here with 4 and negative 2, the 4 is further from 0, so the positive 4 pulls the negative over to the positive side. So when we're doing addition with integers, if the two numbers are positive, then the answer is definitely positive. However, we need to pay close attention to the cases where you have a positive and a negative number. Whichever number is farther away from 0, the answer is going to end up on that side of 0. So if we're looking at 4 and negative 3, 4 is further away from 0, so the answer is going to end up on the positive side, just like we found positive 1. But if we look at 4 and negative 6 is farther than away from 0, so our answer is going to end up on the negative side, which is how we got negative 2. Sometimes memorization like that is helpful, sometimes it's not. So if that felt confusing, just draw up a number line and you can see which side is which. Now this table that we have on the left side, I had a positive number plus a positive number, and then we kept going. But now I'd like to take a look at if we start off with a negative number, can we use this pattern to make conclusions about negatives plus negatives? So negative 2 plus 4. Well, we actually have that answer right here. Negative 2 plus 4, that came out to be a positive 2. Negative 2 plus 3, well, if negative 2 plus 4 was 2, and then we just added one number smaller, this would have to come out to be positive 1. And notice that we're decreasing, so the number we're adding, 4, 3, 2, 1, 0, everything's going down by 1, and so is our sum. So from 2, we go down to 1. When we do negative 2 plus positive 2, it goes down to 0. Negative 2 plus 1, again, we're decreasing. Negative 2 plus 0, decrease from our previous answer, and we can just continue our pattern. Now, at the very bottom here, we have a negative plus a negative, and the answer came out to be negative. And that's kind of equivalent to what we had with positive plus positive is always positive. A negative plus a negative will always be a negative. So if the signs match and we're doing addition, the result will have the same sign. 2 positives equal a positive. 2 negatives equal a negative. This is not the same when we do division and multiplication later, so we have to make sure to keep these rules sorted out in our minds. It's only when you have a combination of plus and minus that you have to pay attention to the sign on the result. For the definition of integer addition, I'm going to refer you to the type up in the book, which is on page 226. I had typed this up and then had a technical issue, so it all erased. So I'm going to talk you through these and then make sense of them, and you can refer to the formal type up in the textbook. So for the definition of integer addition, we are going to let m and n be integers. And each one of the cases, a through e, m and n, are described a little bit differently. So for part A, m can be any integer, and then we're shown that if we took the number 0 and added that to our integer m, the result is still m. So just like normal addition, adding 0 doesn't change anything, so that's good news. For part B, we're told that m is greater than or equal to 0, so is n. And then if we wanted to add m plus n, we would just use whole number addition. Because if m is greater than or equal to 0, n is greater than or equal to 0, then we're adding two positive numbers. This is just like the stuff we've done before we started talking about integers. But it's worth mentioning here because positive numbers are part of the integers, so we have to make sure to cover all of our bases. For part C, we're told that m is greater than or equal to 0, as well as n. But then we're shown the opposite of m, plus the opposite of n. So these are the negative integers. M and n originally are positive integers. They're both greater than or equal to 0. But we're looking at the operation using the opposites of these. So we're adding negative integers here. And this part of the definition says that what we can do is add m and n as if they were positive integers, and then just take the opposite of their sum. So for example, if we had -5 plus -3, we could write this as 5 plus 3 with a negative outside. Either way, we get -8. Part D says n is greater than 0, but also that m is greater than n. So if n is positive, and then m is even bigger than n, then we can write m plus the opposite of n. Remember, n is positive, so the opposite of n would have to be a negative integer. We can use the commutative property of addition to write the opposite of n plus m. Those would be the same calculation. But then we can also write this as subtraction, m minus n. So adding a negative is equivalent to subtraction. And then for part E, we're told that n is greater than m, and that m is greater than or equal to 0. From this one, we can say m plus negative n is again equal to the opposite of n plus m. But then we can write this as the opposite of n minus m. So what I'd encourage you to do to make sure that you understand each one of these statements, pick some integers, m and n, that fit each one of the criteria. So for A, you can pick whatever integer you want, -11. Let's let m be -11, then 0 plus -11 is equal to -11. For part B, you need to pick two positive numbers. Add them together, you'll see it's just like whole number addition. For C, pick two positive numbers, take their opposites, add them together, and show that it's the same as what we have here. For parts D and E, you need to be careful about how you pick m and n. For example, n greater than 0 could be anything, 1, 2, 3, 4, 5, whatever. But then m has to be bigger than whatever you picked for n. So maybe for part D, if we wanted to do a quick example, we could pick n to be 2. M has to be bigger than n, so let's pick m to be 5. Then we could use this rule that says 5 plus the opposite of n, so the opposite of n would be -2. That's the same thing as -2 plus 5, which is the same thing as 5 minus 2, which is 3. All of these would give you the same value, 3. And I encourage you to try E as well. Pick an N and M that you can use to match these criteria, and then test it out with the logic statement that we have following. Absolute value comes into play here. Now that we're talking about positives and negatives, it's worth mentioning absolute value. So the definition for absolute value is the distance between a point corresponding to an integer and 0. So if I wanted to talk about the absolute value of 3, I could put a point on my number line at 3, and I could count the distance from 0. So if 0 is here, I am 1, 2, 3 units away. So the absolute value of 3 equals 3. But if I wanted to talk about maybe -2, I could put a point at -2 and then count how far that is from 0. I'm 1, 2 units from 0. I did go to the left, but notice the absolute value definition does not ask if you went left or right. It just asks how far did you go. So the absolute value of -2 is 2 units. There is a formal definition for absolute value, which says anytime you take the absolute value of a number, it can be broken up into these two rules. We use the top rule if we're looking at a positive number, or 0, and the bottom rule if we're looking at a negative number. So if I'm looking at x equals -7, then I need to use this bottom rule. So the absolute value of -7 is equal to the opposite of -7. The opposite of -7, that's like saying the opposite of an opposite. So remember that -7 is the opposite of +7. So the opposite of -7 sends you right back to +7. If we were looking at x equals +3, then I would say the absolute value of +3, I need to use the top rule. That just says copy your x over because there's no negative here to deal with. All right, we have a few properties and a few theorems that we want to talk about before we finish up on properties of integer addition. Theorem 5.1 talks about the closure property, commutative property, associative property, and the identity. So closure just says if you pick two integers, the result is also going to be an integer. Oopsies. So closure means if you take two numbers from a set and you perform an operation on those two numbers, the result also belongs to the set. It's a little bit more than what we really need to focus on though, so if you want more information on closure, come chat with me in office hours. Commutative property says that you can add things in any order. So if I'm adding numbers like a plus b, whether or not a or b is positive or negative, I can reverse the order here, and the answer is still going to be the same. Associative property says you can add numbers in any order you want using parentheses to group them. So if I have a plus b plus c, each one of these numbers is some integer. I don't know if it's positive, negative, whatever, but I could first add a and b, then add c, or I could add b and c first, then add a. So we can use parentheses here to control the order that we're adding these things, but it doesn't matter because the sum is equal regardless of where the parentheses are. And then lastly, we have the identity. 0 is the identity for integer addition, which means if you are going to add this identity, if you add 0, it doesn't change the value. That's basically the thing we saw on the last slide where we did 0 plus, for example, a, it's still equal to a. So 0 plus an integer, you still get your integer back. Theorem 5.2 talks about an additive inverse. This is actually part of the identity. An additive inverse says that if I take a number and I add it to its opposite, I get the identity back. So an integer added to its opposite is equal to 0, like 5 plus -5, that should be 0, or -7 plus the opposite of -7, which is +7, that's also equal to 0. So integer addition has this additive inverse property. We have one more theorem, that's theorem 5.3, that says the opposite of an opposite, basically they cancel each other out. So this is the double negative idea. So if I'm looking at the opposite of a, and then I take the opposite of that, it gives me the positive integer a back. The addition property of equality, this is also part of theorem 5.3. It says, let's pretend we have two integers, a and b, and they are equal to each other. We can add the same thing to both sides, and they remain equal to each other. This is useful when it comes to solve equations. So for right now, we're just saying equality still holds when we add an integer to both sides of an equation. And then our very last property from theorem 5-3 is that we can reverse distribute these negative symbols. So we have the opposite of A plus the opposite of B. We can pull that negative out and just say A plus B on the inside here. So these are our three theorems for integer addition. Integer subtraction is very similar to integer addition, so we're going to go through this rather quickly. We have a lot of the same models. For example, the chip model. If I want to do integer subtraction, I can again use the chip model to do this. For example, maybe I want to do 3 minus negative 2. Now, the way that this chip model appears is going to feel a little bit different, but it's the same concept as the chip model with addition. I'm going to represent my first number, 3, using the chips that I have. So I'll draw 3 white chips. And then what I need to do is remove 2 negative chips. So minus negative 2 says remove 2 red chips. But if you look at my model, there are no red chips. What we need to do is add neutral pairs so that there are red chips. If there's not enough red chips to remove, we need to add neutral pairs until there are enough red chips to remove. So I'm going to add a neutral pair, 1 red, 1 white. Looking at the value inside of my circle, it still equals positive 3. I've added this neutral pair, which does not contribute to the value of what's inside the circle. Now I added 1 neutral pair, so I have 1 red chip. But I need to remove 2 red chips. So we need to add as many neutral pairs as we need until there are enough red chips to remove. So we need to remove 2, which means I need another neutral pair. Now again, I double check. I've got 2 neutral pairs, so those are like zeroed out. I have 3 positive chips left over. This is still equal to positive 3 in here. But now I can do the subtraction part. So we just set up the model so that we are able to remove the 2 red chips. If I remove the 2 red chips, now I can see that there are 5 white chips left over. Or rather, 5 positive left over. Which means 3 minus a negative 2 results in positive 5. Let's try another example. Let's do negative 4 plus 2. Oh, that's integer addition. Let's do subtraction. If I start off with my negative 4 representation, and it says minus 2, this is subtracting positive 2. So what I have written up here says to remove 2 positives. But if I look in my circle, there aren't any positives. Since there aren't any positives to remove, I'm going to add neutral pairs. Until there's enough positives for me to remove. So 1 neutral pair won't cut it. I go to add my second neutral pair. Now there are 2 positives that I can remove. So I remove those, count what's left. There are 6 negatives left. Which means the result to negative 4 minus positive 2 results in negative 6. Let's compare this to a problem that's easily confused for this. So if I did -4 minus a -2, that's actually saying to remove 2 negative chips. So I start off by representing -4 with red chips, and then I want to remove 2 negatives. Well, in this case, there are 2 negatives ready for me to remove, so I go ahead and remove them, and I'm left with 2 negatives. So -4 minus a -2 leaves me with -2. These two problems look very similar. They have one tiny difference, and that's that I'm subtracting a +2 or I'm subtracting a -2. And notice that the answer is different because of that. So make sure that when you're reading subtraction problems that you know if you're subtracting a positive or if you're subtracting a negative. We can also use the charged field model with integer subtraction, where we use plus signs to represent positive integers, negatives to represent negative integers. So if I wanted to represent a number like -3, I would just put 3 negatives in my circle, and I can always add any amount of neutral pairs, and it doesn't change the value of what I have in the circle. So we can use this to do subtraction problems with integers. For example, -3 minus a -5. Well, the minus -5 says to remove 5 negatives. If I wanted to remove 5 negatives, I can't. There's not 5 there. So I would have to add neutral pairs until there's enough for me to remove 5 negatives. So I add 2 neutral pairs so that I have 5 negatives that I can remove. Once I remove them, I see my answer is +2. Now sometimes we get worried about how many neutral pairs to add. So if that's something that you're worried about, try not to worry because it's fail-proof. If I started off with 3 negatives and I get crazy adding neutral pairs and I add way more than I need, it'll work itself out. So here I've added way too many neutral pairs, but that's okay. I'll still go through and remove 5 negatives. 1, 2, 3, 4, 5. It doesn't matter which ones we remove. Once I cross out my 5 negatives, I'll go through and erase them. And now I need to count the value that's represented in the circle, keeping in mind any neutral pair is really a 0. So any neutral pair I can find, I'm going to circle it and then 0 it out. And I'll do this until there's no neutral pairs left. And I still get the 2 positives remaining. So I get the same answer. So don't worry about adding too many neutral pairs. It's kind of foolproof. Just make sure that you count them up correctly at the end. If I had something like -3 minus 2, for example, I've got 3 negatives, and this is telling me to remove 2 positives. But there aren't any positives in here for me to remove, so I would have to add neutral pairs so that there are 2 positives for me to remove. I'd identify them, remove them, count what's left, see that I have 5 negatives remaining. We can also use the pattern model to demonstrate integer subtraction. 4 minus 3, that's just like whole number subtraction, that's equal to 1. 4 minus 2, that's equal to 2. 4 minus 1, that's equal to 3. 4 minus 0, that's equal to 4. Notice here that we are subtracting one number larger each time. So from -3, we added 1 up to get to -2. From -2, we added 1 up to get to -1. And our answer, they're following that same pattern. So when we do 4 minus -1, we're going to take the previous answer, add 1 to it to get 5, and we can keep counting down, seeing that subtracting a negative sometimes results in a positive. And we could do the same thing with double negatives. So -2 minus 4, we've seen that already. That comes out to be -6. -2 minus 3, that's -5. -2 minus 2, -4. -2 minus 1, that's -3. Notice that the answers are increasing from -6 to -5 to -4 to -3. We can continue this pattern. And something to notice here is that there's different cases. So when we are starting with a negative, subtracting a negative, we can result in a positive. Or if we're starting with a negative, subtracting a negative, we can result in a negative. The best way to determine which sign your answer is going to have is to look at each of the numbers that are involved. So -2 minus -1, the -2 is further away from 0 than the -1 is, so we're going to end up on the negative side. -2 minus -5, well, we're subtracting a -5, the double negatives end up giving us a positive, so it's almost like -2 plus 5, we end up on the positive side. We only have a little bit left in this section, so hang in there. The definition for subtraction of integers basically builds on the definition for integer addition. It says that for any integers a and b, a minus b is a unique integer n, such that I could take n, add it to the integer b, and it gives me a back. So let's think about a couple of integers like -3, and so we'll let a be -3, and we'll let b be 5. If I did a minus b, that would look like -3 minus 5. The result is n, where I could do a equals b plus n. A is -3, b is 5. We just need to figure out what n has to be. Well, if I'm starting with 5, I need to add a number to it so that the result is -3. It would have to be -8. So that's what the definition of subtraction of integers looks like. We do have one theorem for subtraction of integers, and this just says basically that the subtraction of two integers can be written as the addition of the opposite of the number that's being subtracted. So if I did -3 minus 5, I can rewrite that as -3 plus -5. All right, folks, that's it for this last slide. So section 5.1, all about addition and subtraction of integers. The reading assignment has been posted, so make sure that you work on that, as well as beginning the recommended problems for this section. And stay tuned for the second video to come for section 5.2.